So in this problem, I want to draw your attention here to mass A and mass B. They're 2 kilograms and 4 kilograms respectively. And initially, block A is moving this way and block B is moving this way. A is moving east and B is moving north, and we don't know their initial velocities. That's what we want to find out. But what we do know is that they eventually collide and combine together. And then this combination mass continues moving off in this direction at 8 meters per second. And that particular direction is 36.9 degrees north of east, okay? So we want these initial velocities here. And of course, the combination mass is going to weigh 2 plus 4, so 6 kilograms. So the first thing you have to recognize here is that this is a momentum problem because things are colliding. Whenever you have a physics problem where things are colliding, it's a momentum problem. And momentum is mass times velocity. And in particular, this is an inelastic collision. And there are two types of collisions. So elastic collisions, these don't really happen in real life. This is where things bounce off of each other perfectly without deforming at all or sticking together. And in this case, momentum and kinetic energy are conserved. But inelastic collisions, these are more realistic. This is what happens in real life. For example, in a car crash, things deform and partially or completely stick together. And in this case, only momentum is conserved. And that is the key to solving this problem, the conservation of momentum. And that says that the initial momentum is equal to the final momentum. And in particular, we can split this up into the x direction and the y direction. So in the initial momentum in the x direction, we must have that equal to the final momentum in the x direction. Similarly, the initial momentum in the y direction must equal the final momentum in the y direction. So we have a problem here where we're moving in both the x and the y axis. So the first step is to split things up into initial x momentum and final x momentum, and initial y momentum and final y momentum. So the first thing you should notice here is that at the end we sort of have a problem, right? We're moving in a diagonal direction, and we can't really easily split that up into an x and a y direction unless we do some calculations. And it's actually not that bad, we just have to use trigonometry. So whenever you have a horizontal and then a diagonal, you can make it into a triangle, a right triangle in particular. And I made mine look like this. It's a right triangle with that 90-degree angle. And we know the hypotenuse is going to be the value of the velocity, 8, and I'll call this x and I'll call this y. And again, the reason I'm doing this is so that I can split this diagonal vector up into its x and y components, because I have to split the momentum up into the x direction and the y direction to solve a problem like this. So if you do the trigonometry, you know cosine is equal to adjacent over hypotenuse, or x over 8. So we get that this value is equal to 8 cosine theta, and we know our angle is 36.9. So that's how I got this here. This is our final x momentum, right? I'm sorry, our final x velocity, 8 times cosine of 36.9. Similarly, sine of theta is opposite over hypotenuse. So that means when we solve for y here, it's 8 sine of our angle. And that is our final y velocity. So now we're ready to do our calculations. So in the x direction, initially we just had a and b, right? And x was the only thing that we're worried about, and a is the only thing that had any x movement. B had no x movement, so we don't need to consider it. So a was 2 kilograms, and we want to know its velocity, so we'll keep that as a variable. And then the final x momentum we know is this final combination mass. Its mass is 6 times its x velocity, very important, 8 times cosine of 36.9, and this is our x direction conservation of momentum equation. Initial momentum, final momentum. We divide both sides by 2, solve for the initial velocity of A, we get 19.2 meters per second. It's that easy. Then we do the same exact thing for the y direction. So initially, A had no y direction, right? It was just B that had the y direction. So this is the only thing we have to worry about in the initial y direction. We know it's 4 kilograms, and we want to know its initial velocity, so I'll keep that a variable. And we know the final y momentum was this combination mass. Its mass is 6 kilograms, and its y velocity was 8 times sine of 36.9. So we'll put that there, mass times velocity, divide both sides by 4, cancel this out, and the initial velocity of B must have been 7.2 meters per second. So not an easy problem. If you have any questions, please let me know on facebook.com/denovotutoring, and you can also contact me there if you're interested in any tutoring. But thanks a lot for watching, guys, and I'll see you in the next video.